All right, so let's continue. Last lecture we were looking at contacts and their properties, and we looked at contact resistivity, and we also looked at case where current flows laterally through the from the contact through the semiconductor. And so let's look at the properties of metal semiconductor junction in more detail. And we start off with a band diagram. And we've done these band diagrams in considerable detail earlier. So what we show here is the energy band diagram before equilibrium. And we have metal here, and we have the semiconductor here. Most of our discussion will center around N-type semiconductor. And so Fermi energy here is close to the conduction band, electron affinities here, and the vacuum level is flat throughout, right? So that's the pre-equilibrium energy band diagram. And we know how to draw the energy band diagram after equilibrium. I'll not go into the details here. So this is what we end up with. We end up with the Fermi energy, which is now, because it's in equilibrium, is flat throughout. And conduction band, one notes here that the electrons will fall from the N-type silicon into the metal here, Fermi energy being higher here. And therefore, the region here that you see here is depleted of electrons here. And which we see from the fact that the conduction band, the separation of conduction band from the Fermi energy becomes larger and larger as you approach the interface here. All right, so what we get from this particular energy band diagram is, if we look at the diagram in equilibrium, what we get here is that there is a energy barrier, phi b here, between the metal and the semiconductor here. All right, we know that there are a lot of electrons in the metal, close to the Fermi energy here, and conduction, of course, takes place in the conduction band as far as electrons are concerned. So we see that the electrons here, they see a barrier of a height phi b before they can cross over to the conduction band here, right? So phi b of we can see here would be important, and from the simple energy band diagram, what we see here is it's very easy to see that the work function is from here to here. And the vacuum level from the conduction band is electron affinity. So the barrier height is then simply equal to the work function minus the electron affinity. Work function is well characterized for a metal. Electron affinity we know for silicon and other semiconductors is also well characterized. So that allows us to determine what kind of a barrier height we will get when we put a metal on top of a semiconductor. However, things are not as simple as it seems here. Let me show you. So this is the simple theory which predicts that the barrier height should go as the work function of the metal minus the electron affinity. All right. So for a variety of metals, we know what their work functions are. We can calculate what the expected barrier heights are, and we can measure also later on in our discussion. We'll see we can measure also experimentally what this phi b is. So this is what people have found. Take aluminum, put it on silicon. Aluminum work function, let's say, is 4.28. We expect a barrier height of 0.27. Experimentally measured barrier height, 0.7 here. Gold, 5.1. We expect a barrier height of 1.09. Experimentally measured barrier height is 0.79. Titanium, calculated, is 0.32. Experimentally measured is 0.5. Tungsten, 0.54, experimentally measured is 0.67 here. So it appears as if the experimentally measured barrier heights you can see here is not correlating very well with the work function, where we expect phi b to increase or decrease linearly with phi m. But we don't see that here. In fact, we see a lot of bunching around maybe 0.7, around that, 0.7 here, 0.79 here. This is slightly off, but again 0.67 here. A lot of bunching around 0.7 value here. So these are experimentally measured values. And this is what our simple theory predicts, that the barrier height should be equal to the difference between the metal work function and the electron affinity here. So obviously something else is going on. There's something else which also has an impact on barrier height besides the metal work function. Okay. And what that is one of the major reasons for the discrepancy that you see here is what are known as surface states here. Okay, so let me explain what is happening here. So before that, just remember that different work functions implying different barrier heights, they imply different positions of the Fermi energy at the surface. Right? If Fermi energy is there throughout here, but suppose I look at the surface here. Surface of what? The surface of silicon. Because silicon, as you know, starts from here, and that's the end of silicon here. So there's the surface of silicon, and following that there is metal. So this is the surface of silicon, and if I have different barrier heights, what it implies is that the Fermi energy at the surface is at different places, right? Because let's say I measure Fermi energy with respect to the valence band. If I have a higher barrier height, Fermi energy is closer to the valence band here. So the position of the Fermi energy at the surface changes here. Now, what we are saying is that one of the major reasons for discrepancy is surface states here. So what happens is you have a normal conduction band and a valence band, but that's in the bulk of the semiconductor. When you reach the surface, you can see that this is a termination of the lattice. There are a lot of, for example, a silicon here would be bonded to 4 other silicons. But then once you come to a silicon here, it doesn't have neighboring silicon atoms here. So you find that there can be lots of bonds which are not satisfied. Okay. Now, as a result of breakdown of crystal symmetry here, what ends up is that you don't have a well-defined conduction band and a valence band that you see here. You get a lot of states in the energy gap. We saw earlier that whenever you have defects, right, the defects, one of the way what happens is defects manifest themselves as states in the energy gap here. So you can see that the surface, you can imagine that the surface has huge number of defects. Defects, you know, each silicon atom, for example, has so many bonds which are not satisfied, right? So it's like a defect here as compared to a silicon atom within the bulk here. So you have a lot of defects, and these defects manifest itself as states. But these states are there only at the surface. They're not there here in the bulk. So that's why we call these states as surface states here. Now, surface states, now they can be of various kinds. I can have a surface state, for example, let's say if I focus on my attention on this one, I can have a surface state which is donor-like. Donor-like means if it is occupied with an electron, it's neutral. On the other hand, if it is not occupied by an electron, it is positively charged. That's what donor is, right? When the donor gives an electron to the conduction band, it becomes positively charged. So a state can be donor-like, a state can be acceptor-like. Acceptor-like means if it accepts an electron, it becomes negatively charged. On the other hand, if it is without that electron, then it's neutral. Okay, so otherwise it's negatively charged here. So the point is that I have a lot of states at the surface. These states, some of them will be positively charged, some of them will be negatively charged. And we have a concept called neutral level. Neutral level means that if Fermi energy at the surface is equal to neutral, Fermi energy at the surface somewhere coincides with the neutral level, then surface charge is 0. Okay. Typically in silicon, what we take as a neutral level is that the neutral level is close to about 1/3 of the energy gap measured from the valence band here. So what does that mean? It means that if my Fermi energy is here, somewhere here, 1/3 above, then my surface is neutral. Okay, that's what it means here. All right. And the surface states that I'm talking about are characterized by a surface state density, NSS. What does it tell us? How many states are there? It's only at the surface, so we define it in terms of per unit area. How many states are there? Per centimeter square per EV. That's how we define NSS. And in general, you would expect surface state density to vary as you travel within the energy gap. You may find in general that you have a lot of higher number of states close to the band edges and lesser towards the middle, but we won't worry about those details. The point is that there are a lot of surface states at the surface here, and they can be charged, positively charged, negatively charged. If my Fermi energy happens to be at the neutral level, then my surface is charge free. What does it mean? That the donor states and acceptor states, their charges, they balance out, positive and negatively charged balances out, and overall my surface is neutral. Okay, so that's the definition of neutral level here. So imagine that this is the neutral level here, located where? 1/3 of the energy gap from the valence band here. If my Fermi energy coincides with this, my surface is neutral. If my Fermi energy is above it, what will happen? If my Fermi energy is above it, it means those additional states will be occupied by electrons and the surface will become negatively charged. On the other hand, if my Fermi energy is below this one, these extra states will no longer be occupied, the surface will become positively charged. If the Fermi energy coincides with En, surface is neutral. Okay, that's the meaning of neutral, the neutral level here. So every surface will have some neutral level. In this case, we are taking roughly 1/3 of the energy gap here. So now look at it. I have a semiconductor which is N-type. So neutral level is located 0.37. I have a semiconductor which is N-type, right? 10 to the power 16. Is Fermi energy, where is it expected? Is expected in the bulk 0.206 eV from the conduction band here. Now, if my bands are flat like this here, I'm talking about equilibrium. If my band suppose is flat, then Fermi energy would obviously be flat. Fermi energy anyway is flat because I'm talking about equilibrium. So suppose I assume that the bands are flat. Can you see whether that can happen? If my bands are flat like this here, what does it imply? EF at the surface is also here. All these states that you see here, can you see all these states? What will happen to them? For any state below the Fermi energy to a first degree approximation are all occupied. So what will happen to all these states here? They're all occupied by electrons. So, which means that I will have a negative charge. All these, see, if Fermi energy were here, surface would have been neutral. But Fermi energy has moved here. It means that all these states are occupied by electrons and I have a negative charge. How much negative charge? Well, QSS, negative charge will be equal to minus Q. I'm taking a uniform density of states for simplicity. Minus QNSS, EF minus EN. EF is here and EN is here. And we find if I take NSS, surface state density is usually very large, 10 to the power 13, 10 to the power 14. Those are the numbers that we typically use. So I've taken a relatively moderate number here, 10 to the power 13. And we get a surface state charge which is minus 8.6 into 10 power minus 7. But then, where will this charge come from? We are saying that now my surface has a negative charge equal to this. Where will it come from? Where will these charges come from? So I've assumed that my conduction band is here, flat. Fermi energy obviously in equilibrium is flat. Then it means that Fermi energy is here. It implies that there is a charge at the surface. Negative charge here. Overall, remember, semiconductor has to be neutral. So where will these negative charges come from? Where will they come from? Where is the source? The source is the semiconductor itself. So what will happen is that your surface states, these electrons that you see here are free. These electrons will go and fall into the surface states here. So they have to come from the bulk. There's no other source. But if they come from the bulk, then what will they leave behind? Positive charge. So what you're saying is if I have negative charge here and I have positive charge here, what will happen? There'll be a field. What is the direction of the field? Here, and which means that the band cannot be flat. Bands will bend. How will they bend? See, if these are negative charge, there'll be positive charge here. The field is in this direction, so the band will bend up. The band will start bending up. So this is not the correct energy band diagram. It can't be like this here. Because if I draw like this here, it implies a large amount of charge. And that charge has to come from here, from the bulk. Overall semiconductor is neutral. Further, let me tell you, if you have a situation like this is the amount of charge, and the charge has to come from, we are saying bulk. And bulk has how much charge? Bulk has a charge equal to doping, right? So suppose I calculate this, the total charge that you see here, QSS, divided by QND. So I'm asking how much of the bulk has to be depleted. You know, if I take all the electrons from the bulk, right, and put it into my surface states here, how much of the bulk has to be depleted? Because remember, the charge in the bulk is QND. So QND times the distance that has to be depleted to supply this amount of charge, this distance comes out to be 5.4 micron, very large. It's not possible that the surface states, they're capturing all these electrons from not only close, but from distances as deep as several microns. They're capturing all of that and you can see it's not realistic because it's negatively, so all this becomes charged here and therefore the bands will bend up. So a more realistic picture of what is happening is this. Even if I don't put any metal, what I expect is that as the bands bend up, note here, the position of the Fermi energy at the surface starts coming down as it bends up. If it didn't bend, then this was the difference between here and here would be very large. We saw here 0.54. But as it bends up, note that this part also goes up here, and En also shifts up. And therefore, the distance between EF and En starts reducing. As the distance between EF and En starts reducing, the amount of charge required at the surface also starts reducing. So eventually what you find is that there is a band bending here. Why? Because the charges, electrons from here have been captured by the surface states here. And the whole thing is charged, and bands bend like this here. And one can calculate how much is this band bending. Okay. And what you would find is, because there are so many states at the surface, what you would find that if you take doping of 10 power 16, 10 power 17 or whatever, you would find that the Fermi energy at the surface is very close to En. Why? Because if Fermi energy at the surface is far from En, that would require a huge amount of charge at the surface. And that charge cannot be balanced here. Cannot be balanced. You can work out how bands bend. For example, we'll see later on, if the Fermi energy coincides here, how much is the charge here? We can work this out and show that Fermi energy has to be very close to the neutral level. If it's not, then I require a lot of charge at the surface. That charge cannot be balanced by positive charge here. So what is very interesting is, you take a bare silicon and dope it whatever number, 10 power 16, 5 times 16 or whatever, you'll find there's a band bending already at the surface here. And Fermi energy is very close to En here. In fact, in many cases, what people assume is that the number of states are so large that Fermi energy is very close to, is almost pinned to En. Almost pinned to En. And we call this Fermi level pinning at the surface here. Alright, so as I said, any movement of EF away from En would imply a lot of charge which cannot be compensated from the bulk. Okay, so Fermi energy is pinned close to En. So that's something which is happening because of large number of surface states. But then, remember what I said? If you want your normal theory to be valid, what does it require? Different barrier heights. It requires Fermi energy at the surface to be at different places. So your metal and semiconductor, when they come to an equilibrium, they are trying to, create an phi b, which is determined by phi m. But then surface states have their own agenda here. They like to make Fermi energy very close to En. So you are saying that there's one more factor which is determining where my Fermi energy at the surface is going to be. It's not going to be decided by, Fermi energy at the surface is not going to be decided by EF or phi m. Because phi m will try to make this Fermi energy at the surface according to it. If I have larger phi m, it would like to push it lower. Right? And even larger, it would like to push it lower here. Or smaller, the Fermi energy at the surface would like to go up here. So phi m would like to move Fermi energy through the energy gap. But Fermi level pinning says, well, no, my Fermi energy at the surface has to be close to En. Alright. So when we said that the energy, the barrier phi b is equal to phi m minus electron affinity, we were not taking into account the surface states. Now, because surface states come into picture, now there's one more factor which is saying where Fermi energy at the surface has to be. And remember, Fermi energy at the surface is directly related to the barrier height. So one more factor comes in, and depending on which factor is important. If, for example, this factor was very important, extremely important, or no matter what metal I put, Fermi energy at the surface would always be close to En. Because this says Fermi energy at the surface has to be En, and then this becomes the barrier height. In all semiconductors, you would see a barrier height which is equal to Eg minus En. But that's not true. It's not that surface states win all the time. The metals also exert their influence. And therefore, what you have is energy barrier height, which doesn't vary much with the work function, but the work functions do have an influence. And it doesn't, the barrier heights don't obey this simple theory because of the presence of large number of interface states here. There are additional factors. So what we point out is metal work function, of course, has an effect on phi b, not that much. Surface states have a huge influence on what phi b is going to be. Now imagine that I have a silicon And when you deposit a metal on its silicon surface is also very reactive. So usually what happens is a small amount of native oxide also forms. Very thin amounts of SiO2 will also form at the surface here. So it's not that you have a metal and you have a semiconductor. In between, you may have a small amounts of SiO2 also. And so that also has an influence on what the effective barrier heights are. So I'm just pointing out 3 factors that affect my barrier height. One of them is the metal work function. The other one is the surface states. And the third one is I may have some silicon dioxide here, small native amounts of silicon dioxide, which would also have an impact on what the effective barrier heights are. Okay. So let me show you this particular chart from this book by SMZ's book here. So let's look at silicon. So he has tabulated the experimentally measured barrier heights for a variety of metals. Okay. So for example, if I take silicon, if I put silver on silicon, N-type silicon, I get barrier height of 0.83, aluminum 0.81 in this case, gold 0.83, calcium 0.4, cobalt, chromium, copper. In almost all cases that you see, if you just go down, what do you see? No matter what metal I put, I have a significant amount of barrier height. I have a significant amount of barrier height. The common metals are aluminum, gold, copper. You can see here the iron. These all give you a significant amount of barrier heights. So which means what? If I take a metal and I put it on silicon, N-type silicon, I'm going to get a very significant barrier height. It's not that I'll end up with a barrier height of 0.1 or 0.2 or very small barrier heights. I'm going to end up with a significant barrier height. Okay. So these are barrier heights for, note also, these are barrier heights for, if there's a barrier height that you know between, the conduction band, then you know the barrier height for holes also. Because the sum of barrier heights for electron plus the sum of barrier height for holes is nothing but the energy gap here. Okay, so all these are for electron barrier heights and you subtract it from the energy gap and therefore you get the barrier height for holes. Take another semiconductor, gallium arsenide. On gallium arsenide, you deposit silver, you get a barrier height, significant barrier height, aluminum, gold. Again, the message that I'm trying to convey is whatever semiconductor you take, silicon, gallium arsenide, and you put a metal on top of it, you get a huge barrier height. That's a fact of life. Okay. And the barrier height, as I said, is determined by a variety of factors. Work function is one, surface state is another, native oxides are the third here. Okay. So whatever metal I put on my N-type semiconductor, I'm going to get a barrier height. Okay. And these barrier heights we can experimentally determine. Right. So this is the picture that I have. I'm not going to write now that phi B is equal to phi M minus electron affinity. I'm going to say phi B is whatever has been experimentally measured. Okay. So we have this phi B here. We can also determine what is the net band bending in the semiconductor, which we call as the built-in voltage here. All right. So built-in voltage, as we have said, is very easy to determine. This is QVBI. So all that you do is you do a sort of energy conservation. You start from here. You start from this point, go up. So you add in energy phi B, you come down, you subtract in energy minus QVBI, you come down further, minus phi N, and you're back at the Fermi energy. And therefore, from there, you can determine that QVBI is equal to phi B, the barrier height, minus phi N. Phi N is this EC minus EF here. And phi N, of course, is EC minus EF is KT, Ln, density of states divided by number of electrons at this particular point here. Okay, so we know how much is QVBI, built-in voltage here. Now, this is the energy band diagram. When we apply a voltage, we can distinguish between two modes of operation. Forward bias, in which case metal is positive, metal positive with respect to semiconductor, and reverse bias, where metal is negative with respect to semiconductor. The reason why we are calling it forward bias, we'll see that when metal is made positive with respect to semiconductor, you can have significant current flow. When metal is made negative with respect to semiconductor, the current flow is small and constant, relatively constant here. Okay, so let's look at now forward bias and reverse bias here. How do our diode behaves in under these conditions here? So forward bias. All right, so this is the picture in equilibrium. Forward bias, I'm going to apply a note positive voltage to the metal, and semiconductor, I'm going to keep it as it is. Okay, so imagine that metal is made positive, the other end is connected to ground. Okay. So this is equilibrium position. When I apply positive bias to the metal, what happens to energies? Energies will go down. Remember, these are electron energies. So energy is E equal to minus Q times the applied voltage here. So the energy band diagram, now imagine the metal will go down by an amount here. Let's look at the energy band diagram. Here, this is the Fermi energy in the metal. Far away from the surface here, from the interface here, this is where my semiconductor is. So my semiconductor stays as it is, far away, relatively unaffected. So it is here. And metal's energies has been pushed down by an amount of the applied voltage here, QVF here. Okay, so this becomes the energy band diagram when I apply positive bias here. Now metal, is not affected. Its Fermi energy is well defined. There's no problem here. Far away, we are saying as you go far away from the interface here, what we are saying is the N-type semiconductor still is not much affected by the applied bias. Of course, some current is going to flow. It's not thermal equilibrium, but the material is not much affected. It's like in quasi-equilibrium, so we can define EC, EF, EV, everything nicely here. As I come closer and closer, I can't define EF because it's not equilibrium. Okay, but we have shown that we have extended this particular line here and here, and the separation between the two, please note, will be equal to Q times VF. When I didn't apply a positive bias, this EF was coinciding with this one here. When I apply positive bias here, the metal side, the energy is moved down by Q times VF here. And so this difference from here to here has to be equal to QVF here. This side remains the same. This side was grounded earlier. This side is still connected to ground as before. Only this side we have made positive here. So you can see here the net effect of this is, and throughout the barrier height, note that as I apply a voltage to a first order approximation, barrier height doesn't change. Phi b is constant here. So phi b, whatever is phi b in equilibrium, the same phi b is when you apply positive bias, the same phi b will assume when you apply a negative bias here. So the phi b is not something which is changing here. So the voltage here at this, you can see here, if you again start from here, go up here and come down here and then come down here and then back to this particular level, and you keep on adding and subtracting energies, you can see here that the net band bending has become QVBI minus VF. Earlier the band bending here was VBI. Now the band bending is VBI minus VF here. The band bending is reduced. And the more the voltage that you apply, the smaller the band bending that becomes here. Okay, does it make sense? Think of it. Earlier what was happening? There was a negative charge on the metal and compensated by positive charges here. Okay, now you made metal positive. What will it do to the net electric field? See, there was positive charge, there was negative charge on the metal and compensated by positive charge here. You applied a positive voltage here. So overall field is reduced. Reduced field means reduced band bending, right? Reduced band bending here, and which is what comes out from the energy band diagram also. Okay. So what happens now? How do carriers move? Now, note that when you make metal positive with respect to semiconductor, we'll only talk about, it's an N-type semiconductor, we'll only talk about flow of electrons. We'll not bother about holes here. So when you make metal positive with respect to semiconductor, you're basically asking electrons to move from semiconductor to metal. That's what you're saying. This is positive as compared to negative. So you want electrons to move from here to here. How do they move? Well, let's see. An electron starts from here and positive voltage has been applied to the metal. So there's a field, and that causes an electron to move. And the electron starts from here and has to come here. All right. Now go back again and see. There's a flow in the neutral semiconductor here, right? Neutral part. Okay. That should not be a problem. But now, once it comes here, then what does it have to do? It has to go up in energy. There is a barrier. Can you see there's a barrier here? It has to reach this particular point here. And how much is the barrier? VBI minus VF. So that's going to be difficult to cross. You have to go up in energy. So it has to start from here. That's okay. That's not a problem. Then go up in energy and then fall down, which is the bottleneck to current flow, which you can clearly see here. The bottleneck to current flow is not going to be movement here. This is an n-type semiconductor. Doping is 10 power 16 or 10 power 17. That's not a problem here. The problem is going to be this part here. The moment it reaches here, falling down in energy is not an issue. Okay, so that's not a problem. So what controls the current? Is this barrier here. This is what controls the current here. Okay. Now, as I apply more and more positive bias, what happens to this barrier? The barrier reduces. So what do you expect current to increase? Current will increase rapidly. How will it increase? Linearly, square, or what? Exponentially. Why exponentially? Well, let me explain. This is an important point. Why would current increase exponentially? Okay, let me explain here. You're right, current exponentially with voltage. Anything which has to cross an energy barrier, the energy barrier goes as exponent. All right, so let me, because we will encounter this again and again, so let me explain. All right, let's look at a picture in equilibrium. Do we know the number of electrons here? Let's call it number of electrons in equilibrium. E is equilibrium, far away from the junction, okay? Ne. How do we write this? Everybody knows this equation, Ne equal to Nc exponent minus Ec minus Ef by Kt. Ec minus Ef, we are taking it as phi n. Okay? Nc exponent minus phi n by Kt. Everybody sees that. How many electrons are here? Let's call this N0. N0 will be equal to Nc exponent Ec0, whatever is the position of Ec here, Ec0 minus Ef by Kt. Fine, same equation, we are talking about equilibrium. So, we can write this as Nc. Ec0 is equal to Ec here plus QVBI, right? Whatever is the Ec at this point plus QVBI is what is Ec0. So, we've added QVBI. And Ec0 minus Ef, we know is phi n, so we get QVBI plus phi n by Kt. And then rearranging in terms of this, what does it tell us? Number of electrons here is equal to number of electrons here multiplied by minus QVBI by Kt. Alright? So this is an important point. The number of electrons, let's say Ne, we know here, whatever is the doping, that's the number of electrons here. The number of electrons at this point will be equal to whatever the number of electrons are here, exponent minus the barrier height divided by Kt. This is the barrier that they have to cross here. Okay? So now, think about the following. This is the number of electrons here will remain the same. It should not change, far away from the interface. So it is still the same equilibrium value. What will happen when you apply a forward bias? The number of electrons here, the barrier height becomes VBI minus VF. So the barrier height becomes minus Q VBI minus VF by KT. Minus Q VBI by KT, I can write it as whatever was there at equilibrium, N0 equilibrium, multiplied by exponent Q VF by KT. Right? So number of electrons now, anybody sees why I put an approximate sign? Why I did, there's a reason why I put an approximate sign. No, so here I didn't put approximate sign, right? Ne, fine, N0, and N0 is equal to Ne exponent Q VBI by KT. No approximate sign. Now here, when I came here, I wrote N0. So what I'm getting from here is that number of electrons here is equal to number of electrons here multiplied by the barrier. Exponent times the barrier here, right? I'm using the same equation now and saying N0 is Ne exponent, the same barrier here. I used the result from equilibrium and I applied it to non-equilibrium situation, right? There's a crucial assumption here that whatever is the Fermi energy here, it keeps on extending till right till here. Right till here. I can use the concept of Fermi energy starting from here right till here. Okay? Then only I can write like this here. I don't want to go into the details, that may or may not be true. Okay? So this is approximate. But anyway, the result that we are using is the following. What we are saying is, if I know the number of electrons here, number of electrons at this particular point is exponential minus the barrier height. Okay? So we are saying exponential minus QVBI minus VF by KT here. And so this gives us the number of electrons at the surface here will be number of electrons at the surface at equilibrium. and enhanced by a factor exponent QVF by KT here. What is the excess electrons at this particular point? The excess electrons here will be equal to whatever was there in equilibrium subtracted from what is now. And so excess electrons is at equilibrium exponent QVF by KT minus 1. Correct? Excess electrons at this particular point. What would you expect current to depend on? Would current be dependent on? Go back and look at this picture here. How did we say current flows here? Starts from here, reaches here, and whatever number of electrons are able to reach at this particular point, they are collected here, and that's not a problem. So is current going to be determined by how many excess electrons reach here? Reach this particular point here. They started from here, but whatever is the excess that reach here, that excess is what is falling down and then contributing to current. Right? So if you think like that, then you can see here, if my excess electrons goes like this here, my current will also go like that. Okay, I'm not deriving. As I said in the last lecture, there are a number of things that we don't have time to derive, but I'm showing you that the excess electrons at this particular point will go as some electron density in equilibrium times exponent QVF KT minus 1 here. If that's the excess electrons here and these excess electrons are falling into the metal, these are the ones that will contribute to current. And therefore, I'm taking a leap from here and writing that the current would also go as exponent QVF by KT minus 1. With some factors here. Of course, the current would depend not only upon the excess electron density, but their velocities and things like that also. And everything is all incorporated in this particular factor here, JS here. So what we expect then is that as you apply more and more forward bias, the barrier that you see here gets reduced more and more. More and more electrons are able to reach this particular point and then fall in and then contribute to current. And therefore, the current increases exponentially with voltage. Okay? In forward bias. The reverse bias picture is different. Let's look at the reverse bias then. This is the picture again in equilibrium. We start with equilibrium. Reverse bias means I'm making metal negative with respect to the semiconductor. Negative means the Fermi energy is going to move up, but keep in mind the barrier height is going to remain the same. Okay, so with that we draw an energy band diagram in reverse bias here. Fermi energy has moved up compared to the original Fermi energy by an amount of equal to Q times the reverse bias voltage applied. And the energy band diagram now can be drawn in a manner that we have been drawing here. The barrier height then becomes QVBI plus VR. This barrier height has increased. While from metal side you see here, this remains phi b. This doesn't change. You know that from simple work function theory, what is phi b equal to? Phi m minus the electron affinity. Phi m doesn't change, electron affinity doesn't change. And therefore phi b remains the same. From surface state theory, you know that there's a neutral level and Fermi level is pinned close to the neutral level. So again, phi b is fixed here. Okay, so for our phi b doesn't change. We'll talk about it a little later on. To a first order approximation, phi b doesn't change with bias. It remains the same here. And so the bias here, the barrier here becomes larger. Okay, so look at the energy band diagram under reverse bias condition here. Let's see current flow now. Current flow now, because you have made negative here and positive here, you are now asking electrons to flow from where to where? From here to here. Right? From metal to semiconductor now. There's a big difference. Earlier you were asking electrons to flow from semiconductor to metal. Now you're asking electrons to flow from metal to semiconductor. So let's take an electron from the metal and let's move it to the semiconductor. What does it have to do? Electron is here. It has to scale the barrier. It has to scale the barrier, goes up and then go down here. Right? That's how it will flow. What is the critical step? Critical step is scaling the barrier here, because once it scales, then there's an electric field and it has to fall in energy and there's no problem. Right? The critical step for current is this part here. This part here, this slow here, and then there's no issue. Right? So current will be controlled by going over the barrier. Now, as I change the bias, does the barrier change? Doesn't change. So what will happen to the current? Whatever current flows, current will be independent. current will be independent of voltage because this barrier doesn't change with voltage here. And it remains constant. While remember in the forward bias case, this barrier, you were asking electrons to go from here to here, and this barrier was continuously reducing as you apply more and more forward bias. So you can make it smaller and smaller. And so current increases exponentially. While in the reverse bias case, this barrier remains the same. Doesn't change here. Remains constant. Okay, let's look at that in a little bit more detail here. So because of constant barrier, current is independent of voltage. And not only that, because the barrier is large, the current will be very small. While in the forward bias, remember, the barrier I could make it very small. So current could become large. Okay, so now you see rectifying property. If you make metal positive with respect to semiconductor, you're asking electrons to flow from here, and the barrier reduces with the application of voltage and you get large current. While when you're applying negative bias, you're asking electrons to flow from metal to semiconductor. The barrier remains constant. The current remains small and constant. It doesn't change much with voltage. Okay, so you have rectifying behavior. Forward bias, you have a lot of electrons flowing. Reverse bias, you have few electrons flowing from metal to semiconductor. And you have a rectifying behavior here. Okay, let's look at this particular behavior in a little bit more detail here. Consider equilibrium. Now in equilibrium, I've shown you two electrons. You can imagine that what will happen is this electrons from here, some of them will gain enough energy and will cross over here. The electrons here, you have a whole population of electrons. Some of the electrons will gain enough energy and will be moving. If they're moving in the right direction, they may also cross the barrier here. So what is happening in equilibrium is something like this here. This process is happening and this process is also happening. Right? Electrons are going from left to right, they're going from right to left, and the two fluxes are cancelling each other, right? So the two fluxes are, let's call these the flux here. This is, if I take current density and divide it by charge, that's nothing but flux, minus Q. So there is a flux of electrons going from semiconductor to metal, and there is a flux of electrons going from metal to semiconductor, and in equilibrium, they balance each other. This process and this process, they cancel each other. They balance each other. Okay. Now, imagine that you apply a reverse bias. What would happen? What does this flux depend on? This flux depends on electron going here, right? So you apply a reverse bias. What will happen to this flux? It will become negligible because now it has to cross a large barrier. This flux becomes negligible. And what are you left with? Only this one. Only this flux you're left with, right? Which is a constant and continues to flow. So what is happening when you apply reverse bias? At equilibrium, both of them are there, cancelling. As you apply a reverse bias, you cut off this particular part here. You make this negligible and only this one is left. And this continues to flow and gives rise to whatever small current is there. Okay. So this current now that we've talked about, J equal to Js exponent QVF by KT minus 1. I've not talked about Js. But Js, as you can imagine, if you put V negative, what do you get? The reverse bias current here. And reverse bias current is what? Reverse bias current is this factor here, right? So it's like an electron overcoming this particular barrier and flowing here. And this current, an electron overcoming a certain barrier and flowing, is what we call as a thermionic emission current. And again, we don't have time to derive. Js can be written as A T square exponent minus phi b by kt. Let's see whether it makes sense. We can't derive it, but does the equation make sense? Okay. So think of apply a negative voltage and the current flowing is Js, right? Js. Now Js depends on exponentially on barrier. Does it make sense? This current that you see here, it has to overcome the barrier here. And that goes as minus phi b by kt. So it makes sense. This part, the current, there is also a temperature dependent part. All right. So that I'll not try and justify this particular part, A times T squared. But this part is the most dominant part here, exponent minus phi b by kt. A is what we call as the Richardson constant. And for a free, that this process will also occur. Suppose you go back here and you take a metal, right? And you don't have a semiconductor. You take a metal and you have vacuum outside, right? So you don't have any semiconductor, you take a metal and you have vacuum outside. What is the barrier that my electron has to cross to go into the vacuum? the work function, right? The work function. So if you heat it up, more electrons will acquire enough energy to go into the vacuum here. And therefore, as you heat up, what you would find is that the current that is emitted from your metal will increase. And that's how it gets the name thermionic. That as you increase the temperature, more and more electrons gain enough energy and they're able to cross the barrier and flow into free space there. So that's how it gets the thermionic emission current. So right in our case, the electron is overcoming the barrier and going into a semiconductor. If you didn't have a semiconductor, the electron would overcome a larger barrier and go into the vacuum here. And that particular part was very important in the beginning of electronics, when we had vacuum diodes and triodes and all that. They were all based on using metals, heating them up, and they would emit electrons. And the whole, electronics was based on thermionic emission. Okay. All right. So this is the thermionic emission current here. A is called the Richardson constant. When you have a thermionic emission into free space, then you have 4 pi, the mass of the electron, Q times K square, Boltzmann constant, H cube. One can derive these things here. That's the Richardson constant. When you have thermionic emission into a semiconductor, the mass gets replaced. We have seen earlier, in those cases, mass gets replaced by an effective mass here. And so the value of Richardson constant is important. For free space, it is 120 ampere per centimeter square per Kelvin square. For free space, when you have effective masses and all of that, then it increases here by a factor of 2 here. Okay, again, let me emphasize, effective masses are not the same, as there are different effective masses for calculation of mobility, different effective masses for calculation of density of states. So it depends on it's a model. It depends on where you're applying it, and the model changes according to the application. So this is the model that we have now for a current flow in a metal semiconductor contact. As I said, no matter what metal you take and you put it on a N-type silicon, you'll get a barrier. You'll get a barrier, and then the current is in forward bias. The current would increase exponentially with voltage. In reverse bias, the current would be constant. What is the constant current? It is given by this amount here. Okay, so that's the nature of your metal semiconductor contact formed on silicon. We also call it after the name of the person who did a lot of pioneering work. We call it also a Schottky barrier diode here. So we see that this is a diode. This is a diode here, controlled by barrier, and often named after the person who did a lot of work and known as Schottky barrier diode here. Okay, how much time do we have? All right, so we are almost. This is something. All right, so what I've been saying so far is that the barrier height here between metal and semiconductor that you see is a constant. A little bit of more analysis shows you that to a large degree is constant, but changes slowly with field also. So the barrier height that you see here is the barrier height at zero field minus Q F0 4 pi E naught ER. There's a term there. So it reduces a little bit as you change the electric field. If the electric field, this is the electric field at x equal to 0 here. So if you make electric field large, this term will become larger and the barrier height will become a little smaller. But if you work out the numbers, this is in few milli electron volts. So for example, this number can be 0.7 electron volt, 0.7 electron volt, and this could be a few milli electron volts here. So it's a small, so which means that the barrier height does change with voltage, but it changes by a small amount here. For those of you who want to know how this will change, I'll post a lecture notes, small lecture notes on that. You can on your own look through the derivation there. Okay. So let's stop here, and next what we will see here is we have been seeing that there is a barrier, and associated with the barrier there's a region here. You can see that the number of electrons are small, and this region is depleted of electrons here. So there is something called depletion width. So we'll calculate what is the depletion width, and we'll see how depletion widths can be used to make transistors. All right, so let's stop here.